In this presentation, let us discuss basic behind vhdl programming, that is how to write a program, and for that what are the basic elements required and how that is declared. That is, before writing any code, the minimum things which you must know: the structure of that particular programming style or the particular pattern. So for that purpose, in case of vhdl, entity declaration is very important part, because that is going to decide actual what exactly hardware you are interested in implementing. And for that, what are the pins from IC design point of view, what are the pins and what are the ports like you want to define, and how to the in terms of number and as far as the functionality. So for all that, basically you need to know how to declare it first. And as a part of declaration, the very important aspect of vhdl is the standard value logic. So what exactly is supported by vhdl, so that part we will have in this particular presentation. So just one by one we will see. So first of all, let us have what are the basic elements or design units in vhdl. So since it is composed of design units as a language, that design unit is going to represent the logic structure, and it can be compiled separately, saved in independent file or in a library, and conventionally its extension is given as .vhd. So in general it is a .vhd file, and the library is actually inbuilt libraries provided by the tool or the platform are part of your whatever model you are going to develop, or whatever code with the help of that particular module you are going to implement. So mainly there are three main units. First one is called entity, that is a basic element. Also the component, module, everything is coming under this. There will be entity specification, the external interface, symbolically you have to give, and automatically it is going to get binded with the architecture, which is corresponding to the schematic and the actual structure. Packet, grouping of elements defined by the packet specification. So there may be list of objects belonging to the packet, and there will be a description. And the third category as far as unit is considered, that is configuration. That is association of an architecture with an entity. So conventionally, in basic programs which we will be dealing with in upcoming sessions, we have to handle all that with respect to entity. Once it is done, then maybe a small example we will go for using configuration and packet or package, we can call user defined. Then next part is like this. You can have, there will be a design entity, then entity declaration, and for that particular entity there may be a kind of a architecture. While developing the architecture, the basic three modeling styles which we have in vhdl as behavioral, structural and data flow, they are applied. So it is a constructional element. From an external point of view, it is specified by input output signals as far as the entity is considered, and from an internal point of view, it is specified by the architecture. So one entity can have several architectures, that is several versions of internal structure. This is very important feature as far as vhdl is considered. Then next parts corresponds to the declaration, how it looks like. Here you can see whatever name you have to give, you give here first of all name. Entity is a keyword and then name. While giving the name, take care that it should always start with alphabet. Since vhdl is not case sensitive, you can go for uppercase or lowercase. Only this underscore is allowed, but no other symbol, and maybe numbers, but alpha numeric combination can be given as a entity name. Then there are port names, that is A and B, for example here, and this is type of the port. We will have a small discussion after in coming presentation about data types in vhdl, so at that time little more focus I will give. And this is a direction, or it is also called as a mode, that is how exactly that particular port is behaving. And then this particular is a semicolon, which is a part of syntax required. Colon is a separation operator, and port, entity and end, these are all keywords or reserve words, we can say. So this way it is to be declared in the beginning part of the program. This is a small example. So by default, the library IEEE and This is a use clause as a part of syntax used in VHDL program as a beginning part or a declaration part. And conventionally, as I mentioned in the history, there are a number of standards published from 1067 up to 2009. Among all, this is 1164 standard, which is directly dealing with all kind of or taking care of all kind of data types and values as far as VHDL is considered, and even operators and many other features, attributes and all from VHDL language point of view. So that's why it is a default part as a declaration as far as declaration is considered. So use IEEE.stdlogic1164.all. So from this particular, whatever is available, all that is made available, or you can use it, or it is becoming applicable. Now this is entity. Say for example, I have given name here and2 op is, then port for my AND gate program. Suppose I want to write, then there are two inputs, two input AND gate, A comma B is the input. So in is a mode, std logic, standard logic, and Z is out std logic. So here we have this std logic. By the end of this session, you will come to know what do you mean by std logic and what are the options available. Then there is architecture. For example, here the word used is data flow. Here you can have data flow or structural or behavioral. You can refer my video on these modeling styles. So there you will get, you will come to know what exactly meaning of each and every one. In general, or a default is behavioral from tool side, or as a default from the any IAC tool. For example, if suppose I want to make something flow of data with based on some timings or something, so I can make it data flow as a just is a part which we are actually writing, and the name of the entity is appearing here. Then begin is a keyword with which the program starts. In between there will be statements, concurrent statements or sequential statements or process statements or whatever. For example, here as a first simple logic gate program, we have written here A and B, one statement which is a concurrent statement, and end data flow. So this is a style. In coming presentations, or you can refer different programs I will be explaining. So as far as mode is considered, there are three categories. In, that is input port, in mode, out, output port. That means that particular IC is, this is out pin or this is in pin, and there is a possibility of bidirectional. So that is in out. So data can be updated and read inside the component. The name of the port can be situated on the left or on the right side of the assignment expression. In case of in input port, data coming to this port can be read inside the component. The name of the port can be situated only on the right side. So that's why whatever in the previous this particular assignment operator, you can see this is on the right side, which is in, and this is on the left side. So out is always on the only on the left side. That is in the previous example that Z was out and in the left side. And as far as in out is considered, both way it is allowed. And buffer output port, output data can be read inside the component. The name of the port can be situated on the left or on the right side of the assignment expression. This mode should be avoided in the hierarchical structure. So traditionally it is not preferred because it is unnecessarily going to infer additional latch on the wafer. So out of these three, in, out and in out are recommended modes, or the modes for of the ports for direction specification. Then there are types. There are two categories: scalar data types and composite data types. As far as scalar data types are considered, there are different data types like integer, real numbers or floating numbers, physical data, that is measurable something and measure units, and enumerated data as an explicit list of data which we can provide. And under composite type, there are arrays, groups of objects of the same type, and records as an aggregates of objects of different types. So these are the possibilities. Then these are the predefined types like character under enumeration, bit, boolean, real, that is float, real, integer, and time, which is coming under physical. All of them you can simulate, and that's why in sim this column I have done this tick mark indicating simulation can accept all these kind of types. As far as synthesis is considered, so out of this integer is synthesizable, but character, bit, boolean somehow they are not directly synthesizable. Composite data type, so simulation is possible, no doubt synthesis is also possible, but there are some restrictions which you have to take care while declaration and while where you are placing them in the program. And types of defined in IEEE library, this is standard library, so that is predefined types. And under IEEE it is stdu logic, which is unresolved logic vector. This is in simulation available, not in synthesize. This is not synthesizable. And std logic, all the signals, so that is std logic vector, signal vectors, this is simulation as well as synthesis is possible. U logic is unresolved logic, so non-resolved multi-valued signals from or maybe whatever you have in your actual implementation sometimes, so that is taken care. Then these are two categories. One is called unresolved logic and another one is resolved logic. As far as unresolved logic, stdu logic is considered, it is monosource signal. Only one driver can generate one signal. It ensures that two different values will not be assigned to a signal on two different places. This is important. Two different values on two different places are not to be assigned in U logic. And tri-state buses cannot be implemented, need two generators for the same signal. So this is not recommended. As far as resolved logic is considered, this is std logic, where multi-source signals, several generators can generate one signal, used for implementation of bidirectional signals, that is buses. Especially the conflict resolution table in IEEE, it has been given as 0, 1, don't care, and high impedance, and that is don't care and high impedance in terms of 1. So like that, attention on multiple signal assignments when using resolved logic inside the same architecture, this error will not be signaled by the compiler, so you will not get there directly error, and more than one generator is allowed. So you have to take care actually while writing your logic. And as far as these standard logics are considered, this is called multi-value, multi-source signal logic. There are these 9 possibilities or 9 options available. First is called U, that is unknown or it has not been initialized, also alternatively referred as uninitialized. This is simulation is possible for all of them. Second one is X, that is forcing unknown level, strong forcing it will be. So that's why it is going to convert into 1. If sometimes whatever is unknown, by default it will be treated as 1 if it is crossing that particular. Then there is 1, that is forcing 1, level 1, strong forcing, and level 0, that is forcing 0, that is strong 0. So logically there are two categories, weak and strong, wherever considering noise margin very close to whatever strong logic level, so that is treated as if it is 1 then 1, and if it is 0 then 0, and somehow it is on the boundary conditions, then unknown levels or weak, then little lesser, so at that time it will be treated as weak unknown or unknown level weak forcing, that will be converted into W, interpreted in terms of W. As far as high impedance is considered, it is interpreted in terms of Z, especially for tri-state logic or tri-state buffer. You want to show any at any point on any signal, like you want to make it in like neither 0 nor 1 and maybe fluctuating or whatever, then in that case as a safe side you can keep this as an other clause. In even in sequential programming or system design, you can keep this as an other or default clause, that is high impedance. And low, that is weak 0, that is L, and high, that is weak 1, that is H. Actually H and L conventionally we in general use for high and low, but here it is for weak 1 and weak 0, H and L is correspondingly used, and for strong 1 and strong 0 directly 1 and 0 is used. The bit type has only one, that the two values 0 and 1. While this is enough for modeling the specific logic, all the objects are initialized, they can be having this particular bit type. In case of multi-valued logic, that manufacturer dependent, there are some cases, and in general no common standard before 1992 for all these valued logic. IEEE standard is 9 valued logic system defined and accepted by IEEE. These are the 9 values. Additional legal wire conditions are necessary if different driver strengths or high impedance outputs of real hardware drivers are to be modeled. So for this purpose, this has been done. It depends on the synthesis tool whether these additional logic values can be mapped to the corresponding hardware cell in order to avoid hardware overhead. One might think of designating bit positions that may safely be ignored during synthesis. So from that point of view, don't care is used. For simulation purpose, the opposite is desirable. That is value which indicates that something went wrong and needs to be inspected, and that's why it is undefined. In the beginning, several incompatible multi-valued logic systems were defined by different software companies. In order to solve the resulting problem, a standardized 9-value logic system was defined. And when you think about any level, then you can go for this dash, or that is called as a don't care, that is any level. Among these, forcing 0, forcing 1, high impedance, and don't care, these are all synthesizable. Rest of all are non-synthesizable. From simulation point of view, all of them you can simulate. Thank you.